Is that 12 or one already? Okay.
Wow.
Anybody is here? Yeah, another thing is that we need to talk about how to keep, how do we know the audience? I think that's important.
Okay, I think we will talk about it. We're live now.
Oh, okay.
Welcome everybody to the Enterprise AI Virtual User Group. My name is Eyal, and this is Vivian.
Hi.
And
Hi, everyone.
So we have been virtual from the start, and these days all other groups are becoming virtual. We will probably continue to be virtual afterwards. While Vivian runs the local Jacksonville AI user group, which is now virtual as well, but will probably become again a local group, while the virtual enterprise AI group is sort of at least we aim to span from the Americas to maybe to all the way to the Middle East. That's why we do it at this time of the day. So last month we had a presentation by Jerry Carroll from IBM that was showing H2O driverless AI. And we wanted to show you today a little bit of what makes it possible, or some ways that it can become possible. What we saw also after Jerry, when I met Jerry in person, I went and looked with him at the document that driverless AI H2O generates at the end and says what it did. And we realized that actually they say that certain things that are done using a genetic algorithm. So I presume a lot of people don't know about genetic algorithms. So I'm going to talk about it today and show you some things that will explain to some degree how this happens, how genetic algorithm can do things that will control the AI to do what we want it to do. And generally speaking, also, I will show a little bit about supervised learning. I will start with supervised learning, and I will talk about genetic algorithms, and I'll show you how they work together. And hopefully it will all make sense. So I'm going to share my screen now and jump to my presentation. This happens, how genetic algorithm can do things that will control the AI to do what we want it to do. And generally speaking, also, I will show a little bit about supervised learning. I will start with supervised learning, and I will talk about genetic algorithms and that. Okay, Vivian, perhaps try to mute at your end. I hear myself, and I don't think it's coming from me. It's maybe...
Oh, I'm sorry. Yes, I'm done because I also watch YouTube in case we have questions.
Okay, maybe you can just.
I'm sorry for the interruption.
No problem. So this is the beginning of my presentation. So let's just tell you a little bit about myself. My name is Eyal. I will wear my computer glasses now so I can see what I'm talking about. My name is Eyal. I am a software developer. I've been a developer for many years. And even more years than that, I've been an artificial intelligence and machine learning aficionado, you can say. And I do mentoring and consulting in the field. And I also specialize in genetic algorithms, of which I'm going to talk today. And recently, I published that book that you see here, and I will mention a little bit more about the book soon or later, sooner or later, or both. And I also run with Vivian, we host that Enterprise AI Virtual User Group, and I also run the Jacksonville Java User Group for many years now. And in my book, I show how genetic algorithms can solve all kinds of problems. And about chapter 7 of the book, I start showing how genetic algorithms apply to machine learning and artificial intelligence. So actually, what we're going to see today is about what starts chapter 7 of that book, and we will go a little bit into the material of chapter 8, and we will try to cover enough of it to make sense. So let me start by just going back and talking about supervised machine learning, because this is what we're going to cover today. Supervised machine learning is maybe the most common nowadays kind of artificial intelligence that you see in face recognition, for example, when you show your phone your face and it can tell if it's you or not you, or the same thing pretty much with the fingerprint that we had before that. Many examples that exist, and we will see some of them in a minute. So let me just, I'm sure that a lot of you already know what it is and know about it, but I'm going to just cover it very quickly. So we will start from sort of from scratch. So when we talk about supervised machine learning, I hope you can see my slides. Vivian, let me know if you don't see what I'm talking about. I wonder if you see my laser pointer here, my virtual laser pointer. Let me know if you can see it. So we have a model. We always talk about a model, and a model is basically sort of like a box that we don't necessarily know what's inside, but it does a mapping between inputs and outputs, and it maps them a certain way that we want the model to do. What do we want the model to do? We will see in a second, but inside that model, there is some algorithm, there is some structure, and two common ones that are also easier to visualize are a decision tree. There could be a decision tree that takes the inputs and does all kind of branching and if and then eventually comes up with the outputs. Or there could be a neural network that I'm showing you here, which neural network is just made of, this is one kind of neural network that has nodes in layers, and every node is interconnected to nodes in the next layer. And basically, it does all kind of calculations. So we have the inputs, and then all kind of calculations happen, and there are outputs here that get more calculations done on them, and eventually it goes all the way to the outputs. So that can make a very complicated mapping from the input to the output. But we wanted to do the mapping that we want. So we have those parameters at the bottom that are part of the model. Each model has parameters of its own that are being adjusted for the model to do what we want to do. And that adjusting of parameter is called learning. In the case of the neural network, those parameters are the weights. Each node here has weights of inputs. Each input comes in through a weight, and that is how much this input is influential. And as these weights change, the function or the mapping of this network can change tremendously, even by small changes. So there are two kinds of operations that you can do with these mappings. One of them is called regression, and this is where the inputs are mapped to one output, and the output is continuous, is a number that can have different values. The inputs are usually called features, and an example for that is house pricing, for example. So we have inputs that are all kind of information about certain house, like the number of bedrooms, square footage, location, can be many more things, can be hundreds of things, hundreds of features. And what we want to come out of here is a number that says this is the market value of the house. The other use case is called classification, where the features again are just the same kind, could be similar features, all kind of inputs about the problem. But what comes out instead of a number is a decision what type these features belong to. We want one class out of these. So basically, we want one output to go high, the rest of the outputs to go low, and that tells us that this is the output that's most likely, this is the kind that is most likely to be the input belongs to. And an example is, this is the iris classic example. We have 4 features that tell us about the leaves of the flower of the iris. And the model, if it works well, it will tell us what kind of iris it is. There are three different kinds of iris, and it will just tell us it's this one or this one or this one. By one of them going high, and the other two will going low. So the question is, how do we do these parameters? How do we change these parameters to make it do what we want to do? Because if you go back here, so the same network can do all kind of different mappings, can do all kind of other problems. Every time we can take that pretty much the same thing, but change the parameters by learning, so it will do what we want. So each model actually has an algorithm that it comes with. So the neural network usually has the algorithm that goes with it is a backpropagation or something that's related to backpropagation, and it adjusts those parameters. So let's go back here. I'm sorry, I'm jumping around. So what happens is in supervised learning, and that's why it's called supervised, we have some examples that we already know what the output should be. So we have the input and we have the output that we want that to map to. So we tell the network, okay, here are the inputs, and here are the outputs that you're supposed to get. And the network starts with random weights and come out with some weird numbers, perhaps. And then it compares to the algorithm that comes with it, compares to the outputs that we wanted it to have. And it says, okay, these are all kind of differences between this and this. So let me adjust those weights. Let me adjust those weights to make the difference smaller. And we keep doing it. We're showing it more examples, and we repeat it, and it keeps adjusting. That's how the algorithm is specifically designed for that. It changes the weights. So if that model is powerful enough, it has enough parameters, and the algorithm doesn't get stuck, then eventually it will be able to imitate those desired outputs that we told it. So we come to the point where we give it inputs, and the outputs are pretty much the same as what we told it that it's supposed to be. And this is where the training ends. And now comes the real test of the network, where we take new inputs that it didn't see before, but they're generally in the same range and the same type of inputs. And we want it to now tell us what the outputs are without changing anything anymore. It finished learning. And hopefully the outputs that it comes up with are actually correct. They're like what we know they're supposed to be. And this is called generalization, because now it generalizes what it learned. And this is really the essence of learning. If the network is too complicated, or if we didn't show it enough examples, then it might memorize those inputs that we show, and it will do very well on those inputs that it learned. But when we show it some other inputs, it will not get them correctly because it has not seen them before. So that's another issue here that we need to keep in mind. So I had it here. I didn't have to go back. So this is the testing or the validation I mentioned. One way to do that, we can just keep some of the inputs that we know, some of the mapping from input to output that we know in advance. We can put them aside and use them at the end to validate. Or we can do a k-fold. Let's say if we do 5-fold, we basically divide our data to 5 groups, and every time we let the algorithm learn 4, and we test it on the fifth on the fifth group that we didn't learn, and then we evaluate how good it did, and we can then take another 4 and see how it did on the fifth one, and we can do this 5 times, and we can get an idea of how well this network is, or this model is generalizing. So let's look at a particular classification problem called zoo animal classification.
Just a minute. We can't see the slides. Can you put up the slides?
You have not seen slides until now?
No. We have not seen slides at all. I tried to send you private chat.
Oh, yeah. I've been in the whole time without slides. Okay. Do you see the slides now?
Yes.
Okay, that's a shame. I'm going to very quickly go to the beginning. Okay, so this was about me. This is the model. The model has the inputs and the outputs, and it has those parameters that we tune them. Those knobs are supposed to symbolize the parameters that we tune. And this will be a neural network that I was talking about. And what we try to do here is to tune the weights of the inputs that are going into the nodes. So the mapping from the input to the output will be what we want it to be. What goes into the model is called features. And in the case of regression, which is the first use case, the output is a continuous number, like in the case of house pricing, where we have features like number of bedrooms, square footage, location, and what we see is the market value. What we want to see out here is just one number, while in the use case of classification, we have all these features, and what we want to see is that one of the outputs goes high and the other ones are low, which is like in the case of the iris dataset, where we have 4 measurements of the leaves of the iris, and we need to decide which of the 3 types of iris it is. And here I was talking about training. So as we said, this is an example of some neural network that has layers of nodes. And the training here is basically adjusting these parameters that are the weights of those nodes. Each node has weights for the inputs that are coming from the previous nodes. And as we change these weights, we can get the output to be what we want it to be. So we have pairs of known input and output. We show that to the network. We say for this input, we want that output, and then the algorithm that is called backpropagation or something from that family will change the weights a little bit to make the actual outputs more like what we want them to be. And then we show another example, it will do it again, and then we repeat everything and it will do it again. And as I said, if this is a powerful enough network, which in the case of neural network means if it has enough nodes, enough layers, etc., it will be able to eventually give us the outputs that we want for the inputs that we give it. And if it's also not too complicated, if it can generalize well, then now when we show it, when we stop this learning process, we don't change those parameters anymore. If we show it some examples that are not exactly what we showed it before, it will still be able to tell what the right outputs are. And this is the main goal that we have when we train such a model. Any model, basically, we want it to generalize. We want it to do well on new inputs, because otherwise it doesn't serve any purpose. The inputs that we already know are not. We already know. We want to be able to do stuff that we haven't seen before. So, and here I mentioned the cake-fall cross-validation, where when I try to evaluate how well the network or the model generalizes, we will divide the input, the set of known inputs to 5 groups, for example, if it's a 5-fold, and then every time we'll take 4 of them, and the 5th one will be used to test the generalization. The first 4 will be used to train it. It will see the input and the output, and then the fifth group will be used to test how well it does once it's finished training, and then we repeat it 5 times with the different combinations, and we do an average. So that's one way to tell, okay, now we have a good idea of how it's going to do when it goes out there in the world and see things that we haven't seen yet, or didn't have them in the data set at all. So now where I was when I realized that you weren't seeing my slides is that the zoo animal classification, which is a data set, it's a public data set that is available from the UCI archives. And the data set I'm showing you here, this and the next one, and of course the iris one, they're all for learning purposes. They are not so real life anymore. We have much more complicated data sets, and everything is a lot bigger and much more features and usually more examples. But they serve the purpose of testing ideas, proof of concept, and doing things quickly to understand where we're going with it. So the zoo, let me show you. I hope you can see my browser now. Let me know if you cannot. The zoo dataset basically says we have here a bunch of animals, and they have features. The features of the datasets is the name here. If you see that, we are not using the name of the animal, but we're using these features. Does it have hair? Does it have feathers? Does it lay eggs? Here there is how many legs it has, which is these values. Most of these features are either yes or no. And then we want to predict, once we have the features, the result is which type of animal it is, and there are 7 types that are basically like mammals, fish, etc. So the database will say, okay, this animal has hair, has feathers, etc. So it's perhaps one of these guys, and it has 2 legs, etc. So we have those examples, and we want to train a classifier to be able to classify those inputs into one of the 7 outputs. And it will look like that. So we have this model. we put here the features that we said there are 16 features, and then there are 7 outputs, and it will be the meaning of the output is which animal it is. And hopefully one of them is high, the rest of them are low. That's what we want the model to do when it finishes training. And we also want it to be the correct one. So we can go and train it. So I will not do that yet, but I have a program that just takes a particular classifier, which is a decision tree, and we'll train it and we'll get some result. But now comes the question, we have 16 features here. Do we really need all of them? Or the other question is, do we care that, what if we don't need some of them? Do we care that maybe some of them are not really needed? They don't give us any added information, or they don't do any good to us. What do we care? Why should we keep them anyways? More information, the better. But actually, irrelevant or redundant features can affect your generalization, make your classifier less accurate. Plus, if you reduce the number of features, you have everything goes faster, the dimensionality is lower, and you basically get a better and simpler model. And the simpler the model, the better the generalization. That's sort of a rule of thumb. There is something called Occam's razor, which is sort of a general thing about life and science. If you have two solutions they do the same thing, you should prefer the simpler solution because it's more general. If you saw the movie Contact, they actually sort of discuss that, but in a different context. So we want to see if we can not use all those 16 features. Maybe you can use some of them, not all of them. And how do we choose though which features to use? So I'm going to get now to genetic algorithm. Just before that, let's just say that we have 16 features. We can either use or not use each one of these features. So the number of possibilities is 2 by the power of 16, which is about 65,000 combinations. So one option is to go and try every combination possible, or 65,000, which may be possible because 65,000 nowadays is not such a large number. But if you think of more real-life problems, they can have hundreds of features or more, and also the training may be a lot more. We may have a lot more examples, and every time we want to train and see the results, it can be basically impossible or too cost. I forgot the term for it. It will be the cost of it will be cost prohibitive. So we want to find a better way to find only those features that will give us the best generalization and the best performance. This is where genetic algorithm can be a very good way to look for those combinations. Genetic algorithms are very good at finding a needle in a haystack. Basically, you have huge amount of combinations. You want to look for the best combination, and you don't want to just try each and every one of them. This is a task for a genetic algorithm. And how does it work? So let's quickly go through it. It's very, it makes a lot of sense. Let's just say it this way. The ideas are inspired by Darwinian evolution. And it's known for producing high-quality solutions in a reasonable amount of time if you plan it right. And it can go around all kinds of issues that you see in more traditional algorithms. We will not go too deeply into that, but let's see what it means that it uses the principles of Darwinian evolution. The idea of Darwin is that you have a population. So here, instead of trying one solution and just move it around like most other algorithms do and change it a little bit at a time, we have a population of solutions, and we start by random solutions. Darwin says let's look at a certain type of an animal or a being, and what you can see is these things. Each one of them is a little different. They're not exactly the same. And they have a way to pass on to their offspring some or all of their traits and properties. And those of them who are more adapt to the environment, that are more successful, they have more of a chance to actually have offspring. So what happens over time, as generations go by, you will see that those properties who make the individuals in the population more successful, those properties will become more abundant, and more of the population will have those properties, and they will become better at that environment. And then if you go and change the environment, then other properties will be more important. And then after a few generations, those properties will be more expressed. So we're trying to do something very similar. We're trying to start with a bunch of random solutions, and then make a new generation by picking the better solutions and somehow breeding them together and creating the next generation. So we'll see how this works. So like I said here, we start with random, we do some evolution here, where we breed a new solution, we do it for a while, and after a while, if we do a good job enough, then we have the solutions that are the best. And they're the best of what this evolution produced. And hopefully they're actually good solutions. Nobody tells us for sure that these are the best, absolutely best solutions. If we went over all 65,000 solutions there and we found the best one, we know it's the best one because we tried all of them. Here, we may do a lot less than that, find good solutions, and we never know. Maybe there is one other solution that's better, but if we got a good solution, we may be okay with that because we are here into engineering and not perfection. This is more of an inside look at the evolution process. So it has 4 steps. Every time we look at all the solutions, we evaluate them. Then we select parents that will become the parents of the next generation. And as we select the parents, we give advantage to those who evaluated better. And then somehow we breed them together. We do something that's called crossover. We breed them together. And then we also add some mutations, just in case maybe sometime a mutation can give us something we didn't have that is important, that can be successful. So to make it more concrete, let's look at our example of choosing a chromosome, with choosing the features out of the 16 features. So we need to have some genetic representation that will allow us to breed solutions together and do mutations on it. So we want to represent each solution as some kind of a chromosome. Here it's very simple. We can just take 16 binary digits that will be our chromosome, and they represent the solution. How do they represent the solution? Is by each of them represent a certain one of the 16 features, like hair, feathers, etc. If it happens to be a 0, that means we don't use that feature. If it's a 1, that we do use it. So this basically says that this and this and this and this, etc. are used, and the ones that are 0 are not used, and we can go and evaluate it. How do we evaluate it? By removing those columns of the features that we don't use, doing the K-fold cross-validation, and finding the accuracy, and then say, okay, so this combination, the performance of that combination, the evaluation of it is whatever accuracy we got. And then we, after we did it, did you want to say something? I'm sorry.
No.
Okay. So this is just one way to do that. I won't go too far into it, but there are ways to select those who are better. We want to give, when we select the parents for the next generation, we basically do some random. We apply some operation with certain probability. So sometimes we can also select the ones that are not best, but generally the better solutions have a better chance to be picked as parents. So they will be more represented in the parents. And as we have 2 parents, we are now going to create offspring from them. So usually you take 2 parents, you make 2 offspring. And this is very easy when you have binary strings. As you see here, what we can do is, this is called a single point crossover. We take parent A and parent B, we cut them, and we swap the genetic material between them. So now we have these 2 offspring, and we continue and until we feel this way, the new generation, and now we have the new generation. The general idea here, the general intuition here, is that good solutions have good building blocks in them, which are the 1s and the 0s, or the patterns of 1, 0, 1 is like a building block. There are different building blocks. And we are trying to find those building blocks and bring them together. And what the genetic evolutionary algorithm and evolutionary process does is bring all these good patterns together until we get very good solutions that incorporate all this. So let's just talk about mutation. Very easy to do a mutation on a binary string like this. We just pick one and we can flip it. Or you can think of all kinds of other things. You can maybe take two of them and switch them around. And if I show you now implementation of it, I hope you can see my screen here. Okay, I'm not sure what the problem here is. Okay, so by the way, this is software that is used in my book, and we are in chapter 7. So actually all this, if you see here the name of the book, there is a similarly named GitHub repository where you can find all these programs, even if you didn't buy the book. So what I'm going to show you here is the zoo database, the zoo dataset, and there is a class that I wrote here that encapsulate that problem, and it can run a decision tree. You can see the decision tree classifier here, and we tell it what features to use, and it will go and train it and do. When we want to do the mean accuracy, it will go and train it and use we'll do the k-fold that we said, the k-fold validation, and will give us the mean accuracy. So what we can do here is the main program. This is Python, I don't know if I mentioned. This is a Python program. A lot of the machine learning is done in Python because it's very easy, and this scikit-learn library is very, very useful and nice to work with. And it has a lot of what you need already created, and it makes it very simple. So that's why it's such a short class. So what the main class does here is take all one, basically take all the features. It makes a chromosome that is all ones, and then it evaluates this decision tree classifier with those features. And I should have done it already because it takes a little bit to get started. But what we see here, let me enlarge it a little bit. So this is the chromosome basically that we are evaluating here, and it says take all the features. All 16 features are represented here. And when we do that, we use the decision tree classifier, we do the k-fold, etc. We get an accuracy of 90.9. It's not 99, it's 90.9. So it's about 91% accuracy, which is not bad. It looks pretty good. But now let's look at the genetic algorithm that we have here. I use a library called Deep. Do you see that here? This is the library. I'm not going to go too much about how it's implemented. There is a lot of documentation, or my book talks about it more. And we set some parameters here. So we have a population size of 50. So each generation has 50 different, different or not different, they may be the same, but it could be 50 different possible candidate solutions. And we will run it for 50 generations and see what we get. And there are some other parameters. I won't get into the actual implementation, but it does pretty much what we discussed. And every time it evaluates, it actually calls this, it calls the class that we saw before, and it evaluates the accuracy of the model with those features. So if I run that, what you will see that actually here, when we evaluate the accuracy, there is a little bit more to it, but I will mention it later. But what you see here, and I'm going to enlarge it, is these are the generations. And what you see here is the best evaluation that we had out of the 50 that we have here. And it's interestingly enough, you can see that even when we started with 50 random solutions, the best of the solutions is already giving us something that looks better than the 91% that we started with. But the question is, can we get better and better as we go, as generation go by? And what you can see here is it does get better slowly. And it will continue to 50 generations, it's still doing it. What you can see also is that the average of the generations go up. This is typical to genetic algorithms because the general population is doing better. But what we really care about is the best one, because the best one is the one that we're going to use at the end. What we don't want to happen is if you see that the average and the max are the same, they came together, that means that the genetic algorithm converged too soon. And we don't have diversity anymore, which is very important to continue finding new solutions. So as you see it finished here, before we look at it, let's look at the graphic representation of this. I hope you can see this on the screen. This is a graph. The green one shows the average performance as generation go by, and you can see that it generally keeps going up. The red one is the best solution, and you see it goes up and goes up, but then every so often it doesn't change at all, and then all of a sudden there is a jump. And you can actually see that after 25 generations, and you can see this here too, we got the best we could get, and after this we didn't get any better. Also, what you can see here that we had 50 generations. This tells you how many times we evaluated. So of course, the first time we evaluated all 50 solutions, at the same time, 9 of the solutions were already the same exactly as before, so we didn't have to reevaluate them. And generally, we can say that there were maybe 50 times 40 evaluations, so we did 2,000 evaluations instead of the 65 that we would normally do if we had to run a search over all the combinations. And what you see here at the end are the best 5 solutions. And what you can see is actually the accuracy is 0.97. It's not exactly what we saw here, because what I did is I added a small penalty. My idea was we don't just want to find the best accuracy, but if we can get the same accuracy with less features, let's go with that. So as you can see here, all the solutions that made it to the top 5, they all have 97% accuracy. But these 4 solutions use 7 features. The best solution uses only 6 features. And why it is the best? Because I made it win because I gave a little punishment. I subtracted like 1,000 for each feature. So instead of 0.97, it's 0.964. And the one with 7 features are a little less. They were penalized a little bit more. So even though they all have, so the idea of it is just to do some kind of a tiebreaker. So if you have two solutions that give you the same accuracy, the one with the less features will prevail. So that's what happened here. And now you have this solution. So instead of 16 features, we use only 6. And instead of 91% accuracy, we went to 97% accuracy, which in machine learning terms is a huge improvement. Think of it of the error going from 9% to 3%. And if you go back to the slides, I hope you can see the slides, then this is what it says here. And I actually listed what are the six features that ended up being selected. So if you just use these 6 features on this set, you get a very good performance, better than if you use all the 16. Of course, if we now go and change maybe instead of the decision tree, we try to use something else, the result might be somewhat different, but not necessarily. Okay, let's go talk a little bit more about genetic algorithms in general. We saw that we started from the machine learning problems, but actually they started a long time ago with all kinds of other problems, and they can solve a huge amount of different problems. And the beauty of it is usually the solution is very similar. It's just that the problems change. The genetic algorithm is about the same idea, and that's what's so fascinating about it. So one known problem is the knapsack, where you have a bag. You want to pack things into the bag, but they don't all fit. So you need to decide what to pack with you. Each item here has a certain value and also has a certain weight or capacity that it takes. And then you have to find the best combinations of items to put here. And it will be the same if you work at Amazon and you need to take a box and put things in a box, and you have to decide maybe what will go in this box. It's analogous to a lot of problems we have in life. And the solution for this is exactly the same solution that we saw for the features, because this is what is called knapsack 0-1. You either take something or not. So the chromosome here also will be 0-1, 0-1, depending. Each one of these things will be like one of the features that we had, and you have to decide if you take it or not take it. So it will be a string of zeros and ones. It will be exactly the same thing. Here is another problem. It's called the traveling salesman problem, and the idea is you have a lot of cities, and you want to cover all of them. Find a route that goes all of them and will be the shortest route. And this is a solution in this case. And think of it more in nowadays terms. Perhaps you are the Amazon truck now with the boxes, need to make deliveries in different places, and it knows the time it takes to go between 2 places. And then you basically say, okay, so what's the best route to go to all these places and take the least time or the least gasoline? And genetic algorithms can do it very well. Here, instead of zeros and ones, we will have chromosomes that are like 1, 2, 3, 4, 5 that show you the order of the city. So it will say 4, 5, 10, 13, etc. But otherwise, it's very similar. Here is another classic problem: how to put, in this case, 16. It's called the n-queen problem. How to put all these queens on a chessboard without them threatening each other, but you want a queen on each column and each row. So again, it's a huge amount of combinations. If you want to go through all the combinations, it will be just unruly. And if you use a genetic algorithm, it will find it rather quickly. And here is another use case where you have just a function that you want to find the minima of the function, the lowest points. And here we're talking about floating point numbers. And genetic algorithms work for floating point numbers as well. And there are even ways to find all 4 of these at the same time or find them one after the other. But it's a very similar idea, only the chromosomes now are floating point numbers and not binary or integers. Let's go back to machine learning. So what else can you do with machine learning? So the next thing I can think about is called hyperparameter tuning. So we already saw those parameters that were here before. I hope you can caught them when I actually restarted my presentation. And this is what we change when we do the learning. The learning process, as we show the inputs and the outputs that they map to, the algorithm that comes with that model, like the decision tree, will change those parameters. And we don't really know what it does, I mean, unless we are very familiar with it. But we actually also have other parameters that are called hyperparameters. What are those? Let's take a quick look here. Remember that we use the decision tree. Where is the decision tree? Here. If we go there, if we go to the class that's scikit class that implements it, you see here the documentation of the class. So this is it's a long way to go. But what you see here is that it has all kinds of parameters that we can send to it. We didn't in this case, so it used the defaults, but it has something called a splitter, max depth. So this is an integer. It has a max numbers. It explains to you what all these things are. You normally are not aware of them, but there are all kinds of internal parameters of the algorithm, and you can change them. You don't have to use the default ones. And as you change them, it can really change the performance of the classifier. It can completely change the results. And then the question is, okay, so if we use a different value for one of these parameters or for other parameters, this is called hyperparameter tuning. Is how to find the best set of hyperparameters that you set on the algorithms, and you set it before the learning starts. So here is another, this is an adaptive boost. It's also a kind of a tree or a bunch of trees. It's a very powerful classifier, and I just have the documentation for this. It's a more nicely formatted. The reason I'm bringing this up here is just to see that we have different types of hyperparameters. So here we see an integer, the number of estimator that it's going to use, and by default it's 50, but what if we use 100 or 99? Here is a learning rate, which is a float. So it could be 1, it could be 0.5, it could be 0.01, etc. And here is one of 2 algorithms that we can just choose, either this or this. So we have like a categorical variable, a float variable, an integer variable. And we want to now go and find the best combinations, the best combination of parameters, so it will give us the best performance. And how the heck do we do that? We have not just, because some of them are actually float, there could be an infinite number of possibilities. And if you have a lot of these parameters, it could be just a tremendous amount. So one thing that data scientists do, or they used to do, is called a grid search. And again, scikit, the Python libraries, scikit-learn has a lot of means to make this very easy. So you can define grid parameters, and what you do is you create a grid that covers different values. So you say, okay, the estimators can be an integer, so let's try these 10, 20, 30, up to 100. The learning rate is a float, so let's do a logarithmic thing. This actually means 10 by the power of -2, 10 by the power of 0. So it's between 0.01 and the number 1, and 10 numbers in between them, logarithmically spaced. And then the algorithm can be either this or that. So let's just look at those possible combinations. So we have 10 possible NS, 10 of this, 10 of this, and then 2 of this. So it's 200 combinations. We have a grid of 200 combinations of parameter, and let's just search that grid. If the best solution is outside the grid, so be it, but let's find the best solution over that grid. And what scikit-learn is going to do, it's going to just do all of them. We'll go one by one by one. You just launch it here very quickly, very easily. After you define the grid parameters, you do the grid search, and it will just go and do all that for you. So let's quickly start doing it on a problem called the wine problem, and I'll show it to you in a second. So we have a wine data set, we have an AdaBoost classifier here. We will run that, and it will start. So first it shows us that with default value, it didn't go so well. It did declare the accuracy is 64%, and now it's starting a grid search. Meanwhile, let me show perhaps the wine data set. It's not much to look at, but it has 13 features, and it has 3 classes that says what type of wine it is. So each type of wine has different values for these features, and it belongs to one of the groups. So if it's doing the grid search, let's go back to here. And there is another thing that some people do is just do a random grid search. It will just take random points in the grid and try them out and fit. What I wanted to show you is that there is actually a way to do that genetic algorithm. The genetic algorithm, like we saw, can find good combinations. So instead of going and looking for all the combinations possible, let's run a genetic algorithm that will take some combinations, just like we did before. We'll take certain combinations and then take the better combinations, breed them together, and do the same thing. And perhaps we'll find good combinations a lot faster than going throughout the grid. So for example, a chromosome here will look like that. Like it will tell you what this is, what this is, and what this is. And as you go and breed them and mutate them, you can do all kind of things to work with those values. So the same library that I use for the genetic algorithms that's called deep has an sklearn deep, a separate library, but it uses deep internally. And what it does for you, it gives you a very similar interface to the grid search, but you add those parameters that are genetic algorithm parameters that says what is the population size, what is the probability for mutation, etc., and how many generations. And what it will do is instead of searching the entire grid, it will run a genetic search on values from the grid, and hopefully we'll still find a good solution fast, but faster than a whole grid search. So let's go back here, and what we see here is first that the default algorithm, like we saw before, without changing any of the parameters, just taking default hyperparameter values, gave us 64%. When we do the grid search that we saw before, we went over all the 200 combinations, we got a much better score of 93%, and it took about 110 seconds on my computer. And now what we did is we continued and did the genetic grid search, and with the parameters that we saw there, which was only like 5 generations and 20 items in population. So you see that looks a lot like the genetic algorithm that we ran before, has a similar output. And at the end, it found a solution that also was at 93%. So it pretty much found as good a solution. I don't know if it's the same one or not. We can look at it. It's just printed out the other way around. N estimator is 70. Yeah, it actually found the same solution exactly. If you look at the best solution and this best solution, it's exactly the same one. But it found it a lot faster. It found it within 36 seconds versus 110 seconds. So of course, this is more of a proof of concept. These are not like real life numbers, but it shows you the potential of the genetic algorithm to not go to just find a good combination without going through all possible combinations. Now we can go another step forward and say, you know what? Why limit ourselves only to the grid? We really want to search all the possible values, not just what's on the grid, because the best solution might hide in between those things that are on the grid. And now that we have a genetic algorithm, it becomes possible because the genetic algorithm can search the entire space. We're not going to search every possible place that is infinite, but we know the genetic algorithm has a good idea. Just like what we saw here, it's an infinite space, but it can still find the best spots. So the genetic algorithm can possibly find, maybe not the best, but will find maybe better solutions that are not on the grid without taking too much time. So, so I'm going to start that. I have a genetic algorithm here that will do that, and that is this guy. So I'm going to run that while I'm talking about it, because it does take some time. So what we did here is we said, you know what, we still put a limit on it. Let's take all values between 1 and 100 instead of 10, 20, etc. Let's take all values between 1, 0, 1, and let's go up to 100. And the algorithm is just one of these two. So like I said before, this is an integer, this is a float, this is categorical, but we can still combine them all together into the genetic algorithm. And now the chromosomes still look something like this and this and this. We just need to find a way to breed them, to mutate them, etc. And what we do, we have to basically represent them in a certain way, and then when we go to evaluate them, we turn them back into the values that we want the hyperparameters to assume. And there is some translation from a chromosome back to the actual values that are estimators, learning rate, and algorithm type. So for example, algorithm type will be 0 or 1. So when we come back here, we'll take the 0 and turn it into this, or 1 will turn into this, etc. What we see here is still too early. Let's go back here and see what happens here. So the genetic algorithm is moving along. And we can already see, I think, right? What was the best that we could do before? Oh, we don't have it anymore. Or do we? No, we lost it, I think. But I think we saw before that the best solution had the 93%. We're already doing better in the very beginning. We are now we are close to 95%, and it's not like taking forever. Let me enlarge this a little bit. I forgot to enlarge it. So here we did just 5 generations, and we found some numbers. Actually, they are not far away from the grid. They're sort of on the edge of the grid, but they're doing better. So we went from 93% to close to 95%, which is also substantial in machine learning. And if we maybe continue the search further or use larger population, we could have found better solutions. So let's tie it back together and go back to Jerry's presentation from last time. So what we saw there was an example of automated machine learning, which becomes very popular. Now we have several products doing it, and we saw a very good product that is offered by H2O AI. And it basically takes a problem and figures out, you also give it some other inputs like how much time you want to spend, or if it's more important for you to be accurate, then let's say that you say accuracy is important to me and I don't mind that it takes a long time, so let's do that. And then you can say time is important even if it's not as accurate. So you have some trade-offs that you can set. But and you define the problem, but basically it does a lot for you. It will take the features, it will do something called feature engineering. Let's see if I mentioned on this. These are things that can be done automatically. Feature engineering is how to take some features and create other features from them by combining them. It can do feature selection, find out which features are important, which are actually disturbing and add noise. And then it can also say, okay, let's try different models. Let's try decision tree. Let's try neural network. Let's try this type of neural network. And when it comes to neural network, you can also say, okay, let's say if we have the one that we saw all the way before. I won't go back there now, but we saw that it has several layers, and each layer has a certain amount of nodes. It can try different you can try 2 layers, 5 layers, 10 layers, and then in the first layer we have so many nodes, the second layer we have so many nodes. All these are actually kinds of hyperparameters or combinations that you can try. And then you can also stack models on top of each other. You can say, okay, let's start with this model, and on top of it we put the other model, or we'll make an ensemble of several of them that we'll decide separately, but we'll combine the results. And each one of them has the hyperparameters and the structure. So you have actually huge amount of combinations, and genetic algorithms can be used for each one of them or for all of them. And this is where a lot of it is going to. So just looking into the future of automated machine learning, the future and the present and the future, I think we will see more and more. We see some genetic algorithms being used, and it's very likely that they will be used more and more, and there will be more ways that people will find to use it. And I apologize for this typo that I see here. So I'll just go back talking about my book. This is a link to the book, and so it shows you AI application of genetic algorithms, but it will show you first other things that you can do with it, more of how we got there, what are the classic problems that you solve, and all kind of other engineering problems you can solve. And then I think at the end, there is one chapter that's very interesting, and I may talk about it in the future here, that talks about biologically inspired algorithms. Genetic algorithms are only one, maybe the most useful one today, but there are many others, like immune systems, ant colony, particle swarm. We take all kinds of ideas from nature and see it works in nature. We try to see if it can work as an algorithm. And also the chapter 7 is the one that talks about feature selection and supervised learning. Is available for free download. Pact, the publisher of the book, released that chapter for free download, so you can use that link. Or this thing, I put it here because I thought it was cool. You see, usually those QR codes look squarish, and there is one place where you can generate a QR code that looks a lot cooler. It does work. So you can use that if you want to download the free chapter. It will ask you for your email. The email will come to me, and I will not sell it to anyone.
Hey, Mani has a few questions, and I'm not sure you address.
Okay, so we just made it to the questions. Yeah. Maybe I will go back to I will get rid of the screen so I can show, I can look at the questions also in writing. So let me try to do that quickly. Here. Okay. I can also do my okay, what are
the live comments? The last 4, yeah.
Let's see. A set of features is linked to the specific data set we have. Yes. Increasing or decreasing the data set may make the feature list redundant, or yes, I would think that if you decrease the data set, then it might make some of the features less useful because maybe they are less expressed. But you generally don't want to decrease your data set. You always want the features you want to decrease, but the data set, meaning the amount of examples, you always want the most that you can get, unless you really have too much to handle, which is usually not the case. Usually the case is you really want more examples. You're always in a search of getting as many examples that you want. So you get the most data set that the largest data set you can get, and then you try to find the best features for that data set. That's how I would look at that. And okay, so Manny has a comment about how genetic algorithms can beat the permutations, right? And then in your experience, when you're doing these simulations and trying to evaluate each genetic experiment, what is the best sample size to take? I'm not sure about what the sample size means. Is the sample size that we use for validation? Usually, there are generally numbers that you would use for a k-fold validation. 5 is a common number. but I'm not sure if that in all the cases that I've done so far, if you're asking about if we just use part of the database, I actually use the entire dataset. But those were not gigantic dataset. So indeed, you can. I guess you're suggesting here that if we want to save time, instead of using the entire dataset, if it's a large one, we will use a sample of the dataset and use that as a sort of proof of concept to see what the genetic algorithm says to use. I actually have not done that. I would use the entire dataset, but it's a good comment, and I think using 5 or 10%, if you want to do that, that highly depends of how many examples you have at hand. If I would say use as much as you can handle, because it will always be better when you can use more examples. So if you have so much time to spend on it or so much resources, then use the maximum size of dataset that works with that. And then learning rate is always between 0, 1, and 1. Why did I max it to 100? Just for fun, to see what happens, to see what it finds. It could be. I mean, it's not going to break it if it's more than 1. But you're right, it's a good point. You don't usually try a learning rate more than 1. And then sample size for validation. So I'm not sure if this is the same question. So Manny, you can clarify some more if I did not answer your question. Here it is. What do we do with real-time data or data that comes in batches of different sizes and variable features? Well, that's a really good question, because it does show things that happen in real life. So it depends. We always have to adapt the solution to our situation. But if you have variable features and different sizes, then you will have to. It will be a problem also for your classifier in the first place. A classifier should have it's built to take a certain amount of features and work with them. If you now have more features or less features, I don't think there is a classifier that can do that. But it's an interesting thing to think about. Maybe we can come up with a classifier that can handle some features or just has room for more features. But I'm not familiar with anything that was done with that. But we do have the case where we have a real-time basically learning. The learning, let's say that the learning happened, you have a model, you deploy the model somewhere, and now it's starting to do the job. In many cases nowadays, in particular, you try to keep training the model as things happen. Also detect shifts. You can say, okay, you know what? There has been a shift in the input. Let's say yesterday people were doing more, or let's say perhaps the model was based on certain inflation rate. This is how much people were buying. Well, this was the inflation rate, and now the inflation rate is different. Actually, Jerry's example with Walmart, we had some things like that. There could be a storm came and it changed a lot of things in how much people could buy or what they would buy. So if you have features that actually reflect all these things, you can say, okay, when we had the data set, in the data set, all these features were around these values, and now all of a sudden there is a shift and things have changed and the values are different. So there are ways to detect it nowadays. Basically, compare the characteristics of the current data that you have versus the data that you use for learning. And as you detect a shift, you can go and retrain. Of course, you will need a set of trusted examples that you may have to, again, manually take some of the new data and have it labeled again, or have it basically classified by an expert, or just what else you can do. In many cases, you can measure. A lot of the classifiers give you a certain confidence, how confident they are in the decision that they made. For example, when you have the classifier that has 7 outputs and one of them goes high and the other one go low, it still doesn't mean that it's 1 and 0. It could be 0.9, and then the next one is 0.6. And if they are very close to each other, that means that the confidence is not, it's less confident, basically. There could also be a certain amount of confidence per output. That could be more complicated. But where I'm going with it is that what you can do is you can take measurements that where the classifier says that it was confident about, and use them as instead of an expert doing that. and then take samples where the classifier told you that it wasn't confident in particular, and let people classify that, or experts, and then feed it again into a new learning algorithm. So like you said here, you can do it in batches. You can either train it offline. Let's say that while you have one classifier in production making predictions, you collect the data and you train a new version of it, and then you deploy that the next day, or you deploy it at some point. Or perhaps if some of the parameters are basically having small changes, you can just go and change things over time. An interesting thing about actually genetic algorithms is that you can, when you have a genetic algorithm solving a problem, it can keep running. You know, I stopped the algorithm at some point because we wanted to get to a result, and we wanted to do it in a reasonable amount of time. And we took the best solution, but after we took that best solution, we can let the algorithm keep running. And as it keeps running, it will find maybe better solutions, or we can feed now new information into the algorithm. The algorithm basically doesn't really get the new information. It keeps doing the same thing, but the classifier that it builds will get the new information. So now the classifier will perform differently. So as things change, the algorithm will change also the feature that it's maybe selecting, or the hyperparameter that it's selecting, because now the data is changing, the classifier is not doing the same way that it did yesterday. So if you keep it running, you basically can have this ongoing evolution, like it actually happens, like real evolution never really stops. And you can keep doing that. And every so often you go and use those results, and you do an update, and then it will keep running. I see new questions.
Yeah.
Yeah, I can actually now see the questions. How would you compare using genetic algorithms to something like Bayesian hyperparameter optimization? And what consideration might you take into account when deciding between them? This is an excellent question that I don't have an excellent answer, unfortunately. So indeed, Bayesian algorithm is an alternative way, or maybe even a mainstream way to do a hyperparameter optimization. AWS use that as their automated way to do a hyperparameter optimization. Unfortunately, I'm not very familiar with it. Genetic algorithm is more of a Swiss Army knife that can solve a lot of problems, and so it can definitely solve or help us with the hyperparameter optimization. And Bayesian, I think, is somewhat specialized or used. I haven't seen it used for other purposes, but it's used for that. So I would think Bayesian is probably a good solution, but unfortunately, I can't make too many comments. I can say that generally, between genetic algorithms and non-genetic algorithms, or traditional algorithms, genetic algorithm is more resilient to getting stuck in what we call a local minima or suboptimal solution. Genetic algorithm is less likely to get stuck because you breed solutions that are supposed to be somewhat different from each other, and you also have mutations that can sort of jump you out of a place that you're stuck. But you need to take care of that. You need to make sure that your population is always diverse. The big problem of genetic algorithm is when everybody becomes alike, and then you can't really make any progress because you breed them, but you get basically like an inbred family. Everybody is the same. But as long as, and there are ways to make sure that this doesn't happen, as long as you keep your population diverse, you will not get stuck. While other algorithms do get stuck, I'm not sure if Bayesian has a way to not get stuck. What makes the Bayesian particularly useful for hyperparameter? That's the only place I've seen it so far. But I definitely should look more into it, so I will have a better answer. And if I do, when I do, I can put it as a comment in this meetup. So I see more questions from Cody. Referring to earlier question, both of them have the advantage of being smarter than just random brute force search. But wondering of their, talking again about Bayesian versus genetics. So yes, both Bayesian search and genetic algorithm will be better than a grid search or random search. Better in a way that they can be faster than a grid search that is exhaustive search and not completely random. But yes, I don't have a good answer about which one of them is better and why. So hopefully I will have to come up with a better answer and publish that. And Nani says it's a good idea, maybe it's a good idea to use them in an experiment. Right, that's definitely a good idea. And Dan is asking, do you have recommended paper to look more into genetic algorithms? Other than my book, there are many papers. Now, papers are usually not give you an overview. They will assume that you know stuff, or they will tell you what preceded them. And papers will usually take a particular case and they will say something. Okay, we have an idea that will improve genetic algorithms, or will make genetic algorithms useful for this problem or that problem. If you want more than of a broad introduction, I'll go quickly into the history. In the 70s, there was a guy called Holland that came up with a book that basically said everything almost that could have been said about genetic algorithms and a lot of other things related. But most people did not understand that book. It was a little complicated. In the 80s came another guy called David Goldberg, 84, I think, and he came up with a book. I forget the exact name of it, but if you look for David Goldberg genetic algorithms, you will find the book. That became a canonical book that made genetic algorithms very accessible. Everybody understood it and realized how easy it is and intuitive to use it. And I think the University of Illinois in Urbana-Champaign has a lab that this is where this guy was from, and they continue his tradition. And they have what they call the illegal, which is the Illinois GA lab, something like that. And but generally, if you just want to get a good idea overview, you can just find a lot of just posts, a lot of just Medium posts and towards data science and all kind of blogs. I actually don't have it in my blog. My blog is AI for Java, originally geared towards Java people, but now I'm starting to do Python stuff as well. I will have a post there at some point soon that's based also on chapter 7 because they released it to me, but I can also write an article that will summarize it more. And you can find a lot of material. Like if you go into also the libraries, there are libraries in any language. So there is the library that I used here was Deep. There are Java libraries like genetics with J, or genes with J, and all kind of others. And usually they also tell you a lot about genetic algorithms, and they show you examples how they solve problems. So this is a good resource as well. Next question. Oh, that is a remark from Mani. Suggest to look at Git repos. Yeah, and he says that my book is better than papers. And my book has a lot of practical examples. Yes, my book is definitely, that's part of the name of the book, is hands-on genetic algorithms. So you have a problem, you have a solution in Python using the deep library, and it is explained pretty much step by step. And then you can really take that. And again, you can go take the code without buying the book necessarily. You can go take the code and play with it and modify it and break it and whatever you feel like doing with it. Or try to rewrite it in another language, another library. So there is a lot that you can do with genetic algorithms, and it's a lot of fun. And that's at least how I feel about it. Any other questions? Okay, so I think I actually did better time than I thought. I was afraid it would take me a very long time to go through it. I hope I didn't go too quickly. And I apologize for the lapse in the beginning when I went through slides and you could not see them. I thank you for coming here. And we will come back next month, hopefully, with another presentation. I might come back in the future also and do more genetic algorithms related presentation. There is one that I'm thinking to do at some point that has to do with reinforcement learning with genetic algorithms, which is not the normal way that reinforcement learning is being done. But it will teach you about reinforcement learning and also see how you could use genetic algorithms for that. So I might do that in the future. And there could be other things that we will try to do, but in the next 2 months, I think we have other presentations, so you will hear about it soon. I have another comment for Cody. Have you found it easy or hard to integrate with other things like Keras, PyTorch? I did not really do it here in Python. I think it's rather easy, especially in the Python. In the Java, actually, I did a combination of genetic algorithms with the DJL. DJL is a deep learning, sort of built on top of PyTorch or MXNet, but it's a Java library that is an open source project done by Amazon, by AWS. So I might talk about it in one of the next meetings, but I do work, I have a project where I take a neural network that is built with DJL, and I have a genetic algorithms, which is another library in Java, and it controls that neural network, and I really didn't have any problems to combine them together because they're two really. The nice thing about genetic algorithm is that it doesn't really care what the problem is. The genetic algorithm only cares about what the chromosome looks like. And you go and you translate it to the problem. That's why I said that the genetic algorithms almost always look the same, does something very similar in most cases. And the difference between the different cases is how the chromosome is built and how you translate the chromosome to the problem. And it's also called, because of that, a blind algorithm. It doesn't really know what that chromosome represents. It doesn't know, this is a chromosome, this is how good it is. This is another chromosome, so good it is, let's combine them, etc. So it makes it very powerful in general. And also, it does not, another thing that the people say about the genetic algorithm, it doesn't have any preconceptions about the problem. It doesn't take any of your bias. You can pretty much separate what you know about the problem, and as long as you just know how to evaluate a chromosome and see how good it is, the genetic algorithm will do the rest without knowing anything, without caring about anything. So it's completely unbiased in this respect. So thank you, everybody. This was a lot of fun for me, and hope to see you in next month presentation.
Yeah. Thank you, Eyal.
Thank you, Vivian. Bye-bye.
Bye. Okay.